In this lecture, we will discuss applications of Gauss law. This is the second part in continuation of the first. In the first lecture, we have discussed some applications, and now we will extend to some more details. Gauss law has many applications. We have discussed some application in the previous lecture and some we will discuss here. We know that the Gauss law can be used to solve complex electrostatic problems. The problem involving unique symmetries like cylindrical, spherical or planar symmetry. Also, there are some cases in which calculation of electric field is quite complex. If you are having large number of charges or the electric field calculation is complex, that involves tough integration, so it will require a lot of time. Gauss provides an alternative. Gauss law can be used to simplify evaluation of electric field in a much simpler way. We can apply Gauss law in many ways. Like, first thing is, if we want to calculate electric field using Gauss law, choose a Gaussian surface such that the evaluation of electric field become easy. Make use of symmetry to make problems easier. Remember, it is not necessary that the Gaussian surface to conclude real surface. That many times the Gaussian surface do not coincide the real, and it can be inside or outside the Gaussian surface. We can take these steps to calculate electric fields. Now we are discussing some examples from the electric field calculator. We have studied Gauss law applications in several lectures, and here we are discussing several problems or issues of and how these problems are resolved by Gauss law, and we will also discuss some numerical problems in electrostatic and resolution of that problems using Gauss law. There are certain applications based on the above mentioned experiments. One is electrostatic shielding. We can create electrostatic shield on from all the side so that there will be no electrostatic field there, even though the electrostatic field on the outside or on the surface. It is also the process of isolating a certain region of space from external field. It is based on the fact that the electric field inside a conductor is zero. So you can isolate a certain portion by using a conductor. Using a conductor, you can isolate one area to second area. We have also discussed this application. During a thunder accompanied by lightning, it is safer to sit inside the bus or car than in open ground under a tree. The metal body of the bus provides a shielding, electrostatic shielding there, where the electrostatic field is zero. During lightning, the electric field discharge passes through the body of the bus and you will be safe. So these are several applications of the capacitor and the shell that we use. Here, here are some examples. Suppose a shell is contained within another shell B. There is a charge QA on A and QB on the red shell B. We have two shells A and B, and exactly the A is sphere, B the shell, and we apply charge QA on the first sphere A and the QB on the shell. The electric field in the region between these spheres completely independent of QB. The charge on the spherical shell. As we have discussed in the previous examples, then if the charge is distributed on a shell, then inside the shell there will be no effect of those charges. And that is why there will be no effect of this field EB, QB will be on the area between A and B. Between A and B, if electric field will be only by A. So you can think of many applications of this, but it's a very interesting principle. And if anybody asks that it is true or false, yes, it is true. Now take a thin sheet of charge, infinite sheet of charge, and a given sheet has a charge density sigma coulomb per meter square. A positive charge is given on this sheet with this strength. By symmetry, if you want to calculate electric field, then electric field is always perpendicular to the sheet in the outward direction if this charge is positive, and inward if the charge is negative. In our case, the charge is positive, so it should be in outward direction. Now, use a surface that exploits this fact will be a cylinder, also called Gaussian pillbox, and here we can calculate this using the Gaussian surface. You must practice this charges on conductors. If we have a solid conductor on which is placed an excess charge, then in static limit, the excess charge will reside on the surface of conductor. And everywhere the electric field due to this excess charge will be perpendicular to the surface, and the electric field within the conductor will be zero. This gives excellent example. Suppose you have a spherical shell or any box, hollow box, and you supply some charge. Then there will be no charge inside the conductor. All the charge that you will give will be only on the surface. But when you calculate the electric field, the field is equivalent to, as you calculate the electric field from the center, and this gives you a feel that the electric charge is residing on the center if you are taking sphere, but the excess charge will reside on the surface. As we know, the charge is same, so this charge will be balanced by each other, and due to this uh, balancing, it will spread all over the surface because it repel each other also. Whenever we want to calculate electric field, we have to take the perpendicular of to the surface to calculate this. The electric field within the conductor will everywhere will be 0. Take this as a problem. A solid conducting sphere is concentric with a thin shell outer side. The inner sphere carries charge Q1 and the outer shell is Q2, and Q2 is equal to minus 3 Q1. Now the question is, how is the charge distributed on the sphere? How is the charge distributed on spherical shell? What is the status of electric field between these two, sphere and spherical shell? Means R is between R1 and R2 and R is less than R1, inside and between. And what happens when you connect these two? So ultimately we have two, one sphere and one shell concentrating. Now in these two concentric sphere and shell, R1 and R2 radius are given, and the innermost shell have Q1 and outermost shell have Q2 charge. Now we will discuss question one by one. The first question is, how is the charge distributed in the sphere? Remember that the electric field inside a conductor in a static situation is always 0. By Gauss law, there can be no net charge inside the conductor. So the charge Q1 must reside on the outer surface of the sphere, like this. The charge distributed is only on the outer surface. There should not be any charge on the inside surface. The second question is, how is the charge distributed on the spherical shell? We are talking about the outer shell. The electric field inside the shell is 0. We know this. So there cannot be no net charge inside the shell. We know that from the Gauss law, then it can be shown that the inner surface of the shell must carry a net charge of minus Q1. Why we are saying? We are saying to give you some results. The outer surface, when we calculate, the charge is Q1 plus Q2. Q1 is from the first and Q2 from the second. We have calculated these type of things in the previous slides. The Q was in outward direction, Q2 is also in outward direction, both will be added. So you will have Q1 plus Q2 charge. So that if this is there, the net charge on the shell should be Q2. We know this. And the outer shell must carry the charge Q1 plus Q2, so that the shell charge should be Q2. And that is why, to compensate this, the charge are distributed in such a way that the inner and outer shell of the surface, and hence the inner should be minus Q1 of 4 pi R2 square. This should be developed there to compensate the things. We will learn these things in later classes. This may be called as induced charge, and that is why I am having minus sign here. We can also calculate on the outer side, and the outer side this should be Q2 plus Q1 upon 4 pi R2 square. This is given in the question from the beginning, that the Q2 is equal to minus 3Q1. If you place this value here, minus 3Q1 plus Q1 upon 4 pi epsilon 0 R square, 4 pi R2 square, you will get minus 2Q1 upon 4 pi R2 square. This is the value outer side. Now the next question is, what is the electric field at R, small r, when you are calculating less than R1? Less than R1 means inside the inner shell, inner sphere, and between R1 and R2 means outside from the sphere and inside the spherical shell. So this can be calculated. We know this, that electric field inside a conductor is always zero. We have analyzed this in the previous slides. So whenever you are inside the sphere, even in conducting sphere, this will be zero. So this is your first answer. Inside the shell, E will be zero. Now between R1 and R2, the charge enclosed within a Gaussian surface. And so E is equal to K Q1 upon R square. There will be no charge field due to the charge on outer shell, as we know, using the Gaussian law. Now the second question is, what is the field above than R2, charge above than R2? In that case, the charge enclosed will be Q1 plus Q2, and so that field can be done as outside R2, Q1 plus Q2 over R square, or Q1 minus 3Q1 over R square, which is equal to minus K 2Q1 upon R square. What happens when you connect the two spheres with a wire? If we connect sphere with a wire, what will happen to the charges? Charges will move and up to obtain electrostatic equilibrium. And there is no charge on the inner sphere then. And none of the inner sphere on the shell. both will be nullified if we join these two. And the charge Q1 and Q2 reside on the outer surface. Also for all R less than R2, E will be 0. This all is all due to Gauss law. It's a very interesting example. If you have two shells and a sphere and you join these two, all the charge will move towards outer surface for equilibrium conditions. And as we know, there should not be any charge, effective charge inside the shell. So inner surface, there is no charge on the inner sphere, no charge on the inner surface, and all the charge reside on outer surface Q1 plus Q2. For R is greater than R2, E can be written as Q1 plus Q2, and in place of Q2, an uncharged spherical shell conducting has a widely shaped cavity carved out of it. Inside the cavity is a charge minus Q. We have used a spherical conductor or and which has a cavity shape, and there is no particular shape of this cavity, and inside the cavity we have kept a charge minus Q. How much the charge on the cavity wall? If the charge is inside this Q, it is less than Q, exactly Q, or more than Q. The question is, how is the charge distributed on the cavity wall? Uniformly, more closer to minus Q, less closer to minus Q. How is the charge distributed outside the sphere? Uniformly, more charge near the cavity, less charge in the cavity. Whenever we have uncharged spherical conductor has a widely shaped cavity carved out of it, inside the cavity a charge minus Q. Then the charge on the wall is exactly Q. Because by Gauss law, since E is equal to 0 inside the conductor, the total charge on the inner wall must be Q. And therefore minus Q will be on the outside. And since there is no net charge, so we are having inner charge minus Q, so the induced will be plus Q. An uncharged spherical conductor has a widely shaped cavity. Then how is the charge distributed inside the cavity wall? On the cavity wall, it is uniform or non-uniform. The induced charge will be distributed non-uniformly to cancel E everywhere in the conductor, because inside there should be zero field. The surface charge density will be higher near minus Q. So this B is the answer for this. An uncharged spherical conductor has a and the charge distributed outside the sphere we are calculating, then is it uniform? Because outside the conductor the E field always point directly to the center of the sphere regardless of the cavity. Now Suppose we are, I think all of you are aware of this 1D graph generator. We have 1D graph generator machine with a radius of 0.25 meter has been charged up. What is the electric field 0.1 meter away from the center of the sphere? The hint is given. Where are all the charges? Outside. So how much charge is in the center? Since all charges in Van de Graaff machine, all the charges is on the surface, it proves that there is no field inside this. So, and you are saying the Van de Graaff radius is 0.25 meter and you want to calculate charge at zero point 0.1 meter. The 0.1 is less than 0.25, so it is inside the Van de Graaff machine. The charge will be 0. Thank you. In this way, in the series of these lectures, we have analyzed many applications based on Gauss law and their solutions. And I think when you go through all these lectures, you will be able to solve any problem related with Gauss applications. Thank you.